In the realm of statistics, we encounter various probability distributions that model different scenarios and phenomena. Each distribution serves its own purpose, providing us with valuable insights into the underlying patterns of data. Let's explore some of the fundamental distributions: the normal, Poisson, binomial, Bernoulli, geometric, and uniform distributions. Starting with the normal distribution, it is perhaps the most widely known and utilized in statistics. Characterized by its bell-shaped curve, the normal distribution describes data that clusters around a central mean. The beauty of this distribution lies in the central limit theorem, which states that, regardless of the original distribution of data, the means of sufficiently large samples will tend to be normally distributed. This makes the normal distribution crucial for inferential statistics, hypothesis testing, and confidence interval estimation, allowing researchers to make predictions and analyze patterns effectively. Next, we turn to the Poisson distribution. This distribution is used to model the number of events that occur within a fixed interval of time or space, given that these events happen with a known constant mean rate and are independent of the time since the last event. Common applications include predicting the number of emails received in an hour or the number of phone calls at a call center. The Poisson distribution is particularly suited for rare events, making it valuable in fields like telecommunications, traffic flow analysis, and epidemiology, where it helps quantify the occurrence of infrequent but significant events. Shifting gears, we find ourselves exploring the binomial distribution, which models the number of successes in a fixed number of independent Bernoulli trials, where each trial has two possible outcomes: success or failure. The binomial distribution requires two key parameters: the number of trials and the probability of success on each trial. It is widely used in scenarios such as quality control processes, marketing, and survey analysis, where one needs to determine the likelihood of achieving a certain number of successes in a set number of attempts. The Bernoulli distribution, a special case of the binomial distribution, is focused on a single trial. It describes a random variable that has a binary outcome, such as flipping a coin, heads or tails. This fundamental distribution serves as a building block for more complex models, including the binomial and geometric distributions. In essence, it encapsulates the simplest form of random experimentation, providing a framework for understanding more intricate probability distributions. We then arrive at the geometric distribution, which models the number of trials needed to achieve the first success in a series of independent Bernoulli trials. It exhibits the memoryless property, indicating that the probability of success is consistent regardless of past outcomes. This property makes the geometric distribution applicable in situations like determining the number of times a die must be rolled before landing a 6 or the number of attempts needed to make a sale in a sales process. Its simplicity and effectiveness in modeling first success scenarios make it a critical tool in probability theory. Finally, the uniform distribution stands out for its simplicity and equal likelihood across its range. In a uniform distribution, every outcome has the same probability of occurring, leading to a flat, even distribution. This can be seen in scenarios like rolling a fair die or choosing a random number from a specified range. The uniform distribution is foundational in statistics, serving as a baseline for comparison against other distributions and often used in simulations and modeling random processes. Together, these distributions form the backbone of statistical analysis, each playing a unique role in modeling uncertainty and variability. By understanding their characteristics and applications, statisticians and researchers can better analyze data, make predictions, and draw meaningful conclusions from their findings. From the elegance of the normal distribution to the specific contexts of the Poisson, binomial, Bernoulli, geometric, and uniform distributions, the study of probability distributions equips us with essential tools for navigating the complexities of data-driven decision-making. As we progress in our understanding of these concepts, we enhance our ability to interpret the world around us and apply statistical reasoning to a myriad of real-world challenges.